In this video, we will be dealing with alternative to practical questions. And we shall be using some selected topical questions. So, we will be starting with question number 1. That is on qualitative analysis. Qualitative analysis. Solid E was analyzed. E was an aluminum salt. The test on the solid and some of the observations are in the following table. Complete the observations in the table. You have 2 columns, test and the observation. Test on solid. A. Appearance of the solid was white crystalline solid. B. A little of solid E was heated in a test tube. The observation: colorless drops of liquid formed at the top of the tube. C. A little of solid E was dissolved in distilled water. The solution was divided into 4 test tubes, and the following tests were carried out. Test 1. To the first test tube of solution, drops of aqueous sodium hydroxide were added. Excess sodium hydroxide was then added to the test tube. The observation there would definitely be a white precipitate is formed. White precipitate formed. White precipitate formed. White precipitate formed that dissolve and become colorless in excess. White precipitate formed that dissolves and become colorless. And become colorless in excess. In excess sodium hydroxide. So, the observation will be white precipitate form that dissolve and become colorless in excess sodium hydroxide. Test 2. Test 1 was repeated during aqueous, test 1 was repeated using aqueous ammonia solution instead of aqueous sodium hydroxide. When you use ammonia solution, when you use aqueous ammonia solution, what you will have will be a white precipitate, and it is insoluble in excess. We'll have a white precipitate formed white precipitate form. White precipitate form and insoluble in excess. In excess ammonia. In excess aqueous ammonia. So white precipitate form and insoluble in excess aqueous ammonia. So 3, the third test tube of solution, to the third test tube of solution, dilute hydrochloric acid was added, followed by barium chloride solution. Of course, with barium, there's no reaction. 4, to the fourth test tube of solution, aqueous sodium hydroxide and aluminum powder was added. The mixture was heated. Effervescence, pungent gas given off. Turned damp litmus paper blue. It turned damp litmus paper blue. Now, D. What does B tell you about solid E? The solid E contains water. The solid E contains water. E contains water. Or you can say E is hydrated. You can say E is hydrated or E contains water. E. Identify the gas given off in test tube C4. The gas given off, they said effervescence, pungent gas. You know the smell of ammonia gas, pungent gas given off. That turned damp litmus paper blue. So the gas here is ammonia gas. Ammonia gas. Okay. What conclusion can you draw about E? Remember about E. About E. The conclusion we can draw about E. Remember, we said it's a white precipitate form that dissolves and becomes colorless in excess sodium hydroxide solution. Then we said white precipitate formed and insoluble in excess ammonia. Then what conclusion can you draw about solid E? Obviously, solid E could be a hydrated salt or a nitrate. Because nitrate will give ammonia gas. With nitrate, ammonia gas, that turned down litmus paper blue. It's possible with nitrate. Or we can say it is a hydrated salt. So our conclusion here will be that E could be nitrate. E could be a nitrate. E could be a nitrate or a hydrated salt. E could be a nitrate or a hydrated salt. Let's go to question number 2. We are not going to be dealing with rates of chemical reaction. Rates of chemical reaction. A student carried out an experiment to investigate the speed of reaction between thiosulfate, sodium thiosulfate solution, and a dilute nitric acid. Sulfur is formed during this reaction, and the mixture turns cloudy. Experiment 1. Using a measuring cylinder, 100 cm cube of sodium thiosulfate solution was poured into a 250 cm cube beaker. The beaker was placed on a cross drawn on a piece of paper. 20 cm cube of dilute nitric acid was added to the beaker, and the timer started. You can observe it. That is how it is. This is the paper with a cross on it. This is the beaker with aqueous sodium thiosulfate and the acid that has been added to it. And you are observing but from above to see when the cross will disappear. The disappearance of the cross is as a result of the formation of the precipitate here. So now, what is that? The timer. You will look at the time, your stopwatch, and look the time that immediately you add the acid, you put on the time. And when immediately you start timing until when you cannot see through the solution. When you cannot see through the solution to the cross, that means the cross has disappeared. And you stop the time immediately and record the time. That was done. The time until the cross could be seen was taken. The time was recorded in the table. Experiment 1 was repeated using different volumes of sodium thiosulfate, as shown in the table. All experiments were carried out at 20 degrees Celsius. This is the table of results. Experiment 1, 2, 3, 4 to 5. The volume of sodium thiosulfate were recorded. Volume of water that was added there. And the time for cross to disappear was taken in seconds. Now, we have been told here to plot the results on the grid below. Plot the result on the grid below. Draw a smooth line graph. We want to draw a smooth line graph. Yeah, to draw a smooth line graph, we are going to plot the time against the concentration. The time against the concentration, time against the volume, time against the volume of sodium thiosulfate that was used. So now we are going to use the data here. This is the time, and this is the volume of sodium thiosulfate. We will plot it. This is a smooth line curve showing that as time increases, showing that when the volume was 20 degrees Celsius, when the volume was 20 cm cube, the reaction was, the time was still at 98. As the volume is increasing, as the volume of thiosulfate is increasing, what happens with the time? The time for the cross to disappear does what? It decreases. So now you will see that as the volume increases, it means that the concentration, you look at the concentration here, you calculate the concentration of the time, the concentration of sodium thiosulfate, then the time. So our question was just what? Draw a smooth line curve using the data that have been given. So 100, the volume was 100, while the time was 10 seconds. The volume is 100, this is 100 here, and this is 10 seconds here. That's how we plot it like that. Then we'll plot all of them, and the last one was, the volume was 10, and the time for the cross to disappear was 98. The volume 10 is 10 here, is 10, And and the time for this to disappear was what? Was 98. It took 98 seconds. So in that case, this is a smooth line curve that has been drawn as a result, has been drawn based on the data that have been provided. Then two, use your graph to work out the time taken for the cross to disappear when 48 cm cube of sodium thiosulfate, this one has covered it, when 48 cm cube of sodium thiosulfate solution and 45 cm cube of water were used. 48 of sodium thiosulfate, volume was 48 cm cube, and the water was 45 cm cube of water was used. Indicate on the graph how you worked out the answer. Okay, look at the volume of sodium thiosulfate here, and this is 40. Okay, you look at 40. Each of the units is 2 units. This is 42, 43, 42, 44, 46, and 48. You come up here, this is 48. Was 48. Now, you look at on the time axis. 48 on the time axis will be what? It will be 18 seconds. So the time is 18 seconds. Use your curve to work out the time. It will be 18 seconds. 18 seconds. It will be 18 seconds. Okay. So you have to indicate on the curve how you got your answer, because it says indicate on the graph how you worked out your answer. You have to look at 48 cm cube of sodium thiosulfate where the curve is, then look at the corresponding time axis, and you will know the time there. Okay, the experiment were repeated at 40 degrees Celsius. Suggest how the result would differ if this experiment was repeated at a higher temperature, 40 degrees Celsius, instead of 20 degrees Celsius, because initially this was carried out at 20 degrees Celsius. Now the temperature has increased by 20 degrees Celsius, making a total of 40 degrees. Suggest the result and give an explanation. If you look at it at a higher temperature, what will happen? The time will reduce. The time for the reaction will reduce. At a higher temperature, the reaction time will reduce. So we can say reaction time will reduce. The reaction time will reduce. The reaction time will reduce. Now, what is the purpose? The reason for explanation. Reason. This is the reason here I've given here below. I said reaction time. The reaction time will reduce. The reason. At a higher temperature, or when the temperature has increased, what happens? Particles will acquire more energy. Particles will acquire more energy. In other words, you can say particle will acquire energy which is equal to or above the activation energy E.A. This will lead to more frequent successful collision, thereby leading to an increase in the rate of reaction. So I have just said particle will acquire more energy, more frequent successful collision, and reaction rate will be faster. Okay, let's go to question number 3. Question number 3. We have what is this? We have okay. Here we have Question number 3. Separation techniques. Separation techniques. The color present in some black currant sweets can be separated by chromatography. The colors are water-soluble dyes. They are water-soluble dyes. The diagram shows how the colors can be extracted from the sweets. Now we have now what? We have the motor there. There's a motor there and a pistol. There's a motor there and a pistol. There is a tripod there and a beaker with a stirrer, or what we call a glass rod, and there is what we call a funnel. So we have been asked, complete the empty boxes to name the pieces of apparatus that have been used. Okay, let's name them. Naming these apparatus, we can say this is, naming this apparatus, we will say this is motor. This is motor. Okay, this is a glass rod or stirrer. We can say glass rod. Or what we call stirrer. You can call it a stirrer or you can call it a glass rod. And you can call this a funnel. Okay. Now, that is a motor, that is a glass rod, and that is a funnel. Now, complete the table. We have done that. The apparatus below was used to carry out the chromatography. This is the apparatus for the chromatography. Now, we are told the apparatus below was used to carry out the chromatography. You have it. It is in a glass. A beaker, and you have the solvent there. You have the paper there. There is a dot there. That is the dye. There is a chromatography paper. That is the chromatography paper. Now, and there is a lid, or what we call the glass cover. Now, name the solvent that is being used. The solvent that is usually used for this is water. Water is always used as a solvent to separate these colors. We can call it water. The solvent is water. Now, they say 2, label with an arrow the origin on the diagram. This is the origin on the diagram. This black dot here is the origin of the diagram. Oh, this is the dye. This is the dye that is going to be used to separate the color, the dye from the sweet that we are going to use in separating the color. So this is the origin, or what we call the dye. Then C part of it. The C part of it. Sketch in the box. Sketch in the box the chromatogram. Sketch in the box the chromatogram. You would expect if 2 different colors were present in the sweets. Okay. Remember, this is the box. This is the box that has been given. This was the box that was given. Now, this is, I have used this to draw. This is the dye, or this is the origin. This black spot here is the dye, which is up here. This is the paper. This is the paper. This is the dye, which is the black spot here, and we call it the origin. Then this is the pencil line. This is on the pencil line. The dye is on the pencil line. Then as water goes up, what happens? The water will separate the color. As water is moving up, it does what? It separates the color. The first color is the green color. Color 1. Then the second color here is the blue color, which is color 2. These are 2 different colors present in this dye. Okay, let's go to qualitative analysis. Question number 4. Qualitative analysis. The different salts D and E were analyzed. Two different salts D and E were analyzed. D was an aqueous solution of iron 3 chloride, and E was a solid. The test on the salt are some of the test on the salt and some of the observations are in the following table. Complete the observations in the table. We have the test and we have the observations. A. The appearance of solution D. Two different salts, D and E. Okay. Appearance of solution D. What do you think should be the appearance of solution D? D was an aqueous solution of iron 3 chloride. D was an aqueous solution of iron 3 chloride. And E was a solid. So what is the color? What is the color of an aqueous solution of iron 3 chloride? The color is usually the color of iron 3 chloride is usually as yellow, could be yellow, yellow, or depending on the concentration, yellow, it could be brown, or orange. This color, the appearance of this is usually yellow, brown, or orange, depending on the concentration. So now, appearance of solid E. Solid E is a white crystal. Solid E is a white crystal. Now they are telling you, test on solution D. Remember, solution D is iron 3 chloride. Now, the solution was divided into 4 equal portions in test tubes. And the following tests carried out. 1. Dilute hydrochloric acid was added to the first portion of the solution. And then aqueous barium chloride. As I told you, with barium chloride or barium sulfate, there's no reaction. The reaction with barium chloride, there's usually no reaction with barium chloride. There's no reaction. So what you will observe, your observation will be, there will be no reaction when it has to do with barium chloride or barium sulfate. So in this case, there will be no reaction. No, you can say no reaction. No reaction. No reaction, or you can say no change. You can say no reaction, or you can say no change. Okay. Dilute nitric acid was added to the second portion, and then aqueous silver nitrate. With aqueous silver nitrate, the aqueous silver nitrate it always helps to precipitate. So when dilute nitric acid was added to this iron 3 chloride, to a portion of iron 3 chloride, followed by what? Followed by aqueous silver nitrate. What is usually going to be formed will be what? A white precipitate. There's going to be a white precipitate of this that is going to be formed. Iron 3 chloride with silver nitrate, there is a reaction between the iron silver and the chloride ion, forming a silver chloride. The silver ion and the chloride ion will react, forming silver chloride, and that is a white precipitate. So there will be a white precipitate that will be formed. White precipitate formed. White precipitate. White precipitate formed. Okay. White precipitate formed. Okay. An excess of aqueous sodium hydroxide was added to the third portion. Now it's going to be the reaction of sodium hydroxide into this portion of iron 3 chloride. Aqueous sodium hydroxide plus aqueous iron 3 chloride. What will you observe? What you will definitely observe here will be brown. A brownish precipitate is formed. A brownish precipitate formed. So we can say brown precipitate formed. Brown precipitate formed. Now, if you go again further, an excess of aqueous ammonia was added to the fourth portion. Now we are now reacting iron 3 chloride, aqueous iron 3 chloride with aqueous ammonia. The reaction of aqueous iron 3 chloride and aqueous ammonia. The reaction will be a brown precipitate. There will also be a brown precipitate with ammonia solution. So there will also be a brown precipitate. Brown precipitate formed. Now, we want to use by the solid now. We now go, there were two salts. One was solution and the other one was salt. E. Test on solid E. The test on solid E. The test on solid E. Okay. C1. Solid E was heated in a test tube. The gas given off was tested. And what was the observation of the gas that was given off when solid E was tested? The gas it turned lime water milky. The gas that was given off on heating solid E turned lime water milky. And that gas that usually turns lime water milky, you know, it is the test for carbon dioxide. It's a test for carbon dioxide. Okay. 2. Dilute nitric acid was added to solid E in a test tube. What was observed? There was rapid effervescence. Rapid effervescence. And the gas that was also released also turned lime water milky. There was always evolution of carbon dioxide. Therefore, the question now reads, identify the gas given off in test C1 and test C2. So the gas there, as I've been telling you, is carbon dioxide. Carbon dioxide gas. Okay, it's carbon dioxide gas. Now, what conclusion can you draw about solid E? Remember, when we're reacting a reaction of acid and carbonates, when acids they react with carbonate, there is always an evolution, or there's always a release of carbon dioxide. When acid react with carbonates, because we are told dilute nitric acid was added to solid E, and there was effervescence, and the gas release was turned lime water milky. That means it was carbon dioxide, implying that it was a carbonate. So we can conclude that it is a metal carbonate. A metal carbonate. Our conclusion is A, E is a metal carbonate. It's a metal carbonate. It's a metal carbonate. Says E is a metal carbonate. And an example of this metal carbonate is Ag. I can say sodium carbonate. I can say sodium carbonate. Or I can also say it could be calcium carbonate. It's a metal carbonate. Now, let's go to the question number 5. Question number 5. Question number 5. The table shows the mass of some ions present in a 500 cm cube bottle of mineral water. There are 3 columns there. Name of the ion, symbols, and the mass of the ion. We have calcium, we have magnesium, we have nitrate, we have potassium. Their symbols are there, and the different masses of the ions are presented. The question A, state the name of the following ions. These ions, the name of the following ions. This is a Cli. This is what we call what? It is a chloride. This is a chloride. Not chlorine, it is a chloride. Then this other one, SO42 minus, it is a sulfate, not sulfate. This chloride ion. Okay, state the name of the following ions. This is chloride and this is sulfate. Okay, calculate the mass. B. Calculate the mass of magnesium ion in 100 cm cube of this mineral water. Magnesium ion. Magnesium ion. We are going to calculate the mass of this magnesium ion. And we are told, ions present in 500 cm cube. The total volume is what? It is 500 cm cube. 500 cm cube will contain 11.6. 500 cm contain 11.6 milligram of magnesium ion. Then they are telling us to calculate the mass of 100 cm cube of this very mineral water. So let's see how we can solve this problem. The way to solve this problem is simple. Let's do it like this. Simple proportion. We can say if 500 cm cube, a 500 cm cube mineral water contains a 500 cm cube mineral water contains 11.6 milligram of magnesium ion. Then they say we should calculate the mass of magnesium ions in 100 cm cube. Therefore, 100 cm cube of the very mineral water will contain X. And what will be the value of X? X will be equal to what? Cross multiply will be 16. Oh, sorry. It will be 11.16 11.16 11.6 milligram. 11.6 milligram times 100 cm cube times 100 cm cube divided by 500 cm cube. And what will be the value? We will have to cancel out the units. This one will cancel this one. And what will be our value? Our value will be, our value here will be 2.3. 2.32 milligram of M magnesium ion. That will be our answer. Our answer will be this: 2.32 milligram of magnesium ion. Okay, describe the test. Describe the test for nitrate ion. Describe the test for nitrate ion. You know the test, the test for anions and the test for cations. We have treated the test for anions and the test for cations. In terms of, in case of a nitrate, we can say, because with nitrate you have to react with aqueous sodium hydroxide. So the test for nitrate will be what? We can say add aqueous sodium hydroxide followed by aluminum. When you add aqueous sodium hydroxide, you now add aluminum. Usually it's aluminum foil. Aluminum foil, now you heat it gently or you warm it gently. There's usually an evolution of a gas. And that gas, if tested with a litmus paper, it will turn damp red litmus paper blue. So that is the test for nitrate. So precisely we can write that. We can write that for the test for aluminum, a test for nitrate, we can say at aqueous sodium hydroxide. Sorry. Okay. I said add aqueous sodium hydroxide. Add aqueous sodium hydroxide. Add aqueous sodium hydroxide followed by aluminum. Usually this aluminum foil. You can say aluminum foil. Aluminum foil. And warm gently. And warm gently. And warm gently. The gas release turn red litmus paper blue. And warm gently. That's the test. I said add aqueous sodium hydroxide followed by aluminum foil and warm gently. The gas released turn down red litmus paper blue. Usually it is an ammonia gas that is always released. The test for nitrate is usually produces ammonia gas. Okay, let's proceed. You have 2 marks there. The gas produced in this test turn red litmus paper blue, just as I told you. State the name of the gas. Simple. Ammonia. Ammonia gas. Ammonia gas. NH3. Okay, D part of it, the D section of it. D section. The apparatus shown is used to get pure water from impure mineral water. The apparatus shown is used to get pure water from impure mineral water. Look at the apparatus as it has been displayed. You have the mineral water, heating, you have 3 boxes. Now, complete the diagram by putting the correct labels in the 3 boxes. Okay. What are the labels? The label here, this is a round bottom flask. This is a round bottom flask. So we can say round bottom flask. You can say round bottom flask. Round bottom flask. Now, this is a condenser. We can label this condenser. You can say condenser or condenser tube, no problem, it's okay. See the same thing, condenser. Now, this is what? This is distilled water that has been collected. So we call this distilled water. Distilled water. Or you can say pure water, no problem. Distilled water. Or pure water, you can put it. Since we want to get pure water from impure water, can say pure water. Okay, that is the label. That is 1. Then describe how this apparatus separates pure water from dissolved ionic solids. How can this is mineral water? This is mineral water with the different ions. This is mineral water with the different ions. How can we now obtain pure water and set aside the ionic solids? The first step is heating this. When the mineral water is being heated, it evaporates. When the mineral water is being heated, water will be converted, liquid water will be converted to what? To steam. And this water will boil at a temperature of 100 degrees Celsius. Water boils at a degree of 100 degrees Celsius. So when water is being heated, the water will boil at 100 degrees Celsius and be converted to water vapor or steam. And the steam will now pass into the condenser. And within the condenser, the steam or the water vapor will condense and now drip off and enter into the conical flask as distilled water. See it here. I said, and this process is called simple. This is a simple distillation. I said this is by simple distillation. Boiled water evaporates as steam or water vapor, at a lower temperature, 100 degrees Celsius, than the ions. When it evaporates as steam at a lower temperature than the ions, then the water vapor enters into the condenser, where it condenses and drip off into the conical flask as distilled water. The solid ions remain at the bottom of the flask. That is what is required of you. So that is it. So we are now going to the general concept. The general concept here. General concept and titration. The general concept and titration. That is question number 6. A solution of calcium hydroxide in water is alkaline. Which one of the pH value below is alkaline? Of course, put a ring around the correct answer. Put a ring around the correct answer. So it should be noted that at the pH sorry, we did not do the last section. We did not. Sorry, please. Sorry. We did only the description on how to obtain pure water from dissolved solids, ionic solids. The third one was water purity. Water purity is important in everyday life. Water purity is important in everyday life. Describe one other area of everyday life where purity of substances is important. Beside water purity, which other thing is important, or which other thing is important for purification in our everyday life? It should be noted that in our everyday life, there are a lot of purification that we need to undergo. We have to do drinking water purification, drinking water, drinking water purification is needed. There is also foodstuff purification of foodstuff. Because they say, describe one other area of everyday life where purification is needed. Purification is needed for drinking water. Purification is also needed for foodstuff. Purification is needed for drinking water. Purification is needed for foodstuff to avoid food poisoning. Purification is also needed for drugs. Purification is also needed for drugs. Purification is also needed for medications. Our medicine or our medication must be pure. Our medication must be pure. So medications. And again, we need pure air. Our air must not be polluted. So we also need pure air. Purification is needed for air purification. So we need purification is needed for drinking water. Purification is needed for foodstuff. Purification is needed for drugs. Purification is needed for medications, and even for the air we breathe every day. So you can choose any of them. So let's get back again to the general concept, a test on general concept and titration. Which one, I say a solution of calcium hydroxide in water is alkaline. Which one of the pH values below is alkaline? Okay, put a ring around the correct answer. Now, you know that a pH of 3 is acidic. A pH of 6 is still acidic. Very, very weak acids. You know that a pH of 7 is neutral. And above 7 to 14, the pH is increasing. And that is what we call alkalinity. The alkalinity is increasing. So, they say which one of the pH value below is alkaline. So, we are going to circle pH 11. pH 11 is the right answer. pH 11 is the right answer. Which of the following is the common name of calcium hydroxide? Tick one box. Calcium hydroxide is not cement. Calcium hydroxide is not limestone. No. Calcium hydroxide is not quicklime. No. But calcium hydroxide is slaked lime. Slaked lime. That is calcium hydroxide. So this one is the right answer. Now, okay. Some farmers use calcium hydroxide to control soil acidity. Why is it important to control soil acidity? It is important to control soil acidity because some plants do not grow in acidic soil. Plants will not grow in acidic soil. Even if they grow in acidic soil, their yield will not be good. Plants will grow properly, but in alkaline medium, in alkaline soils. So, why is it important to control soil acidity? It is important to control soil acidity because plants do not grow in acidic soil. You can write it like that. Or you can say because plants grow well, but in alkaline soils. So that you can write that. Then just put it the way I have put this one. You can say as I said, plants grow well. I say plants grow well. Plants grow well. Plants grow well in neutral soil, in neutral soil. Or plant do not grow, or plant die. Or you can say plants do not grow well in acidic soil. Plants grow well in neutral soil, or plants will die in acidic soil. You can put it like that. Plant will die. Plants will die. Plants will die in acidic soil. So just say that's the reason. Plant grow well in neutral soil, or plant will die in acidic soil. So it is important to control it. Okay, acid rain can cause soil to become acidic. Acid rain can cause soil to become acidic. Describe how acid rain is formed. We have 3 marks for that. How is acid rain formed? Now, let me give you a brief explanation on how acid rain is being formed. You know, it starts from fossil fuels. It starts from fossil fuels. Sulfur that will result in the formation of acidic gas comes from fossil fuels. So I write sulfur from fossil fuel burns in oxygen in the air to form sulfur dioxide. This is the equation. The sulfur dioxide will react with oxygen in the air to form sulfur trioxide. This is the equation. Sulfur dioxide or sulfur trioxide dissolves in rainwater to form acidic rain, usually sulfurous acid. This is the equation. So sulfuric acid is what we call the acid rain. This is how they are formed. So for the purpose of revision, you should know that when fossil fuels are burnt, they produce sulfur. The sulfur that is being produced react or burns in oxygen to form what we call sulfur dioxide. The sulfur dioxide will react with oxygen in the air to form sulfur trioxide. Either the sulfur trioxide or the sulfur dioxide will dissolve in the atmospheric water vapor, in the atmospheric water. In the air, the sulfur dioxide will mix with the rainwater. When the sulfur dioxide or the sulfur trioxide mix in the air with rainwater, it forms what we call sulfurous acid, and which will now fall on the surface of the earth as acidic rain. And that's how the equation has been given to you. Let's proceed. Okay, you have 3 marks for that. Calcium hydroxide reacts with hydrochloric acid to form a calcium chloride plus water. Calcium hydroxide is alkaline. It's alkaline. And hydrochloric acid is that is alkaline. You are right. You are now reacting. This is like an acid. This is an acid-base reaction. Acid-base reaction, resulting in the formation of salt and water. And they are telling you, state the name of this type of reaction. The name of this type of reaction between alkali and acid is what we call neutralization reaction. This is a neutralization reaction. This is a neutralization reaction. Neutralization. This is a neutralization reaction. Okay, let's proceed. A dilute solution of calcium hydroxide can be titrated with hydrochloric acid using the apparatus shown below. This a dilute solution of calcium hydroxide can be titrated with the hydrochloric acid using this apparatus here. In this apparatus, this is what we call, this is the burette. There's the acid in the burette. There's acid in the burette. This is the conical flask. And in this conical flask, there is a solution of calcium hydroxide. The question reads, describe how you would carry out this titration. It is simple. The first thing is you will add in the conical flask, you are going to add 2 or 3 drops. You are going to add 2 or 3 drops of the indicator. You can use any type of acid-base indicator, but I would prefer you use phenolphthalein indicator. You are going to use a dropping pipette. You are going to use a dropping pipette to add 2 or 3 drops of phenolphthalein indicator into the conical flask. Secondly, using a 25 ml volumetric pipette, you are going to pipette a calcium hydroxide into the conical flask. Thirdly, you are going to take the initial burette reading of the acid in this. You are going to take the initial reading of the acid in this one. Then you will now titrate slowly by adding acid from the burette into the conical flask. until the indicator changes color. Then finally, you will take the final, you will record the final volume of the acid that has been used. Once more, I said, using the dropping pipette, you are going to add 2 or 3 drops of phenolphthalein indicator or any other acid-base indicator into the conical flask. Using a volumetric flask, a volumetric pipette, you are going to pipette 25 ml of the calcium hydroxide solution into this conical flask. Then thirdly, you are going to take the initial burette reading of the acid in this burette. Then fourthly, you are going to open the tap and add acid from the burette into the conical flask until it changes, until the indicator changes color. And when immediately it changes color, you take now the final burette reading of the acid. That is how you can describe how you can carry out this titration. This is how I've presented here to you. I've said using a dropping pipette, add 2 to 3 drops of phenolphthalein indicator into a conical flask. 2, using 25 ml volumetric pipette to pipette calcium hydroxide solution into the conical flask. 3, take the initial burette reading of the acid. 4, slowly add acid from the burette into the conical flask until the indicator changes color. Finally, record the final volume of the acid added. Thank you for listening. For those of you who haven't subscribed to this channel, please like this video, share to other learners, and most importantly, take some time and subscribe to my channel so that subsequent solved question will come directly to you. Thank you very much. Thank you.